Hello everybody, welcome to the webinar about rectifier technology. We will start in about 1 minute on time, so we will start in 1 minute. Well, welcome again. Thank you for joining us this afternoon, at least in Europe. I understand people are also listening from other parts of the world. Before we start, a couple of housekeeping rules. You will be muted during the webinar, but there is a question box or a question mark. You can enter your questions at any time during the webinar, and at the end of the webinar, we hope we will be able to answer all of them. If not, you will receive a follow-up email, and also you will receive a follow-up email anyway to request for the presentation. There will be a second date for the webinar, so after that we will choose the best recording, and also recordings will be available for everybody. The webinar will take roughly 50 minutes, and before we start, I also should tell you that my name is Jos van Loo, and I work in the power management industry for about 35 years now. So here we go. We promised you this agenda about the transient thermal impedance and the package choice, or the back end, also the front end processes for rectifier. So those will be the two main topics. We're going to also talk about planar Schottky, zero defects. Before we go, we're going to have a 2 or 3 minute introduction of Taiwan Semiconductor, because a lot of people, the webinar was advertised via Bodo, and actually we know that not everybody knows Taiwan Semiconductor, so we'd like to introduce Taiwan Semiconductor a little bit. We know that rectifiers tend to be a low-tech subject and that type of stuff, but we hope we can surprise you today with some interesting information. That's our target, and after all, rectifiers are the highest volume power semiconductor component in the industry, and as Bodo said in his introduction, the world would not work without them. So here we go, Taiwan Semiconductor. In the top right hand of our slide, you see that we are 40 years old in Taiwan. Maybe important to mention, as most of our listeners are in Europe, we are also more than 20 years here in Europe, offering support in sales, customer service, logistics, technical support, and quality. We are a $227 million business in rectifier, or in semiconductors, I should say. We have a printer division that is a partner of us, that's also owned by Taiwan Semiconductor, and of course we are predominantly focused on rectifiers and a few other components, as we'll see. We have 4 production sites internally, and those are pure rectifier manufacturing sites. The key thing to mention here is that we are not only 20 years in Europe, but we have more than 20% of our revenue in Europe, so we think we are successful here in Europe. Our product portfolio covers the entire range, or not the entire range, but 95% range of the rectifier business, which we manufacture in-house. We have also 2 design teams, one for MOSFETs and one for LED lighting ICs, and now also for power management ICs for automotive. So those are our key activities. Important to mention, of course, is that not only 67% of our products are AEC qualified, but we are actually focused on the automotive market, which has an above average percentage of our sales. Here we go. This was the brief introduction, and the marketing part is now over. Now we're going to the technical stuff, and first we're going to talk about transient thermal impedance and the package choice. We actually choose to talk about packages first. These days, a lot of people talk about processes, front end. In rectifiers, the picture is very balanced, which means that from a cost perspective, the back end is about the same as the front end, depending a little bit on the component. And as a result, there is also less differentiation possible on the front end by having different processes. So that's why we're going first here to the back end here, and we're going to look at the entire back end, but we're going to revisit the situation on surface mount packages. This situation has been around for 3 to 5 years, 3 years roughly. And I think we're updating it with our latest available information about these packages and where we think they might be going. On the top line, you'll see 3 packages that are important: the micro SMA, the SOD123W, and the SOD123HAE, with the exposed pads on the right-hand side. The one in the middle there, the sub SMA, is just there for completion. It's not a package we currently focus upon. The bottom side, just to put everybody on the same page, we have, starting from the right-hand side, SMC, SMB, and SMA. The workhorses, these packages are more than 30 years old, and as a result, well established. The other ones there, the SOD128, is a little bit newer here. When you see the footprint size, there are various ways of defining that. We define it by multiplying the length with the width and the height. Oh, sorry, the length and the width, obviously. But obviously, if you take, for example, include the protruding tabs and the minimum recommended solar pads, the SOD128 is pretty much similar to the things like that. So that is the case. I've seen a message here that the organizer is having technical problems. I hope the webinar will not end it, but I will continue as we do speak. So the internal drawings, SMA, SMB, and SMC, on the left-hand side are the historical packages. The ones with the flat lead packages are over there. So as we compare them, actually, sometimes it's difficult to look at these things. The blue thing is the chip, in this case, on the left-hand side. As you can immediately see that the ratio of the chip to the complete footprint is kind of small in these packages, and that's historically because they're more than 30 years old, and that reflected actually the old molding tools and lead bending capabilities. So what you see on the right-hand side is the flat lead packages. They look a little bit more elegant. We're going to see if that really brings you a lot as a designer. But obviously, the path for the heat to get out of the die into the PCB is slightly shorter, and that's what you really want from a thermal perspective. Now, there's only so much you can do because also the width is important in these lead frames. So if you make them less wide, then actually you also increase the thermal resistance. So this is the capability, or how these packages compare. We'll go now to the next slide here, and we're going to compare this later on. This is our view, and then we're going to compare this later on with your view. So what we have is the 4 key things for our perspective is from day one, people complained about the height of the SMA and SMP. So the package height is an important criteria. We have transient thermal impedance and thermal resistance. Both are different and will lead to 2 different solutions from our perspective. And of course, there are over the years improvements have been made to also reach CR defects here in our package development, and that relates predominantly to solar voids. Now here is your perspective, or here we have to ask the question is, how can we help you? On the left-hand side is thermal resistance. I made a pie chart. It's completely random. I put 20% for the package. It depends a little bit. Some people use 5 by 5 millimeter solar pads. That's roughly 20%, and maybe if you use the minimum recommended solar pads, then the PCB is going to be more like 85%. But if you use multi-layer PCBs and that type of stuff, you can get it down to a lower value. So here, the message is essentially we can only provide a small contribution here when it comes to thermal resistance. We'll talk a little bit more about it later on. When it comes to transient thermal impedance, and it's an important factor actually here, we talk everything less than 1.5 millisecond. Now, some of it, you know, depends a little bit on the die size, could be 1 millisecond, could be a little bit more, roughly. So there's a lot of things here that are less than 1 millisecond. I'm just talking about the surge you experience when you turn on a flyback converter. It might be 300, 400 microseconds or shorter, or a lightning strike, which might be 1 millisecond or even shorter. So in this case, it's the die size that is really combined, of course, with the contact area that really determines, you know, how to deal with these surges. And then you just take an existing die and actually you put them in a smaller die package here. As you can see, you can take the SMB, put it in SMA or an SOD128, and you know, you get a similar performance when it, you know, of course, you know, with a good die attach, you get a similar performance in these smaller packages. So here, downsizing is actually an interesting prospect. This picture here, I would like to ask you first to go to the bottom of the slide. The bottom of the slide, you see 3 package names: SOD128, SMA, and SMB. Now, you can actually make these tests in various ways. The gentleman that made this test in our headquarters was a fan of the SMA. So in this setup, he favors the SMA, because if you look on the left-hand side, he uses the minimum recommended solder pad of the SMA, and he puts the other packages on there. So you can do these experiments in various different ways, and then other packages will look better. But the main thing, of course, is the main message of these things is that a reduced package size will always increase the temperature. This is just unavoidable thermodynamics. So if you actually here, you see that the SMA and SOD128, you actually have a fairly similar performance on their recommended solder pads. SOD128 might be even a little bit better, but then of course you increase the size. And you're getting a difference, let's say, around 15 degrees C. I should mention here that this test was done at 1 amp on a standard rectifier. So you're talking about a 1 watt power dissipation roughly, and thermal resistance in the area of 100 degrees Kelvin, 100 Kelvin per watt. But then, you know, this is one thing as we are talking here is, you know, let's not look at this as a black and white result, things like that. Smaller is worse or that type of stuff. The question is, who puts a 1 amp through an SMA standard rectifier? I would say very few people do. If you take it and put it in a flyback converter, you know, you might put in 100 milliamp through it, and then actually you have your 30 amp surge that determines whether you use the S1 or a bigger die. So in Schottky, yeah, it could be, if you're looking at a Schottky application, people could easily dissipate half a watt here in these type of packages, and then these differences might be important. But it's not, you know, it's not like black and white or on and off or something like that. It's very analog here. It's like, you know, if you go down from the SMB down to an SOD123 package, you might get a difference in 30 degrees or in 30 Kelvin per watt, I should say, or 35 Kelvin per watt. Is that important? Definitely. If you take half a watt, you know, people don't want their design to become 10 degrees hotter or 15 degrees hotter. Now, if I use an application where I dissipate 100 milliwatt, which is not unreasonable for these packages, if you just need the big surge and you just put 100 milliamp through them, well, then you're starting to talk about differences between 3 and 4 Kelvin per watt, or 3 or 4 centigrade. I'm not going to tell anybody how to design anything, and everybody has his own threshold level about which type of temperature increase is acceptable. But as you can see, there are various ways these things can play out. So some people will be able to downside their application or get a higher power density, if you want me to use that word, and other people's won't. It will be your decision in the end, and your quality thinking or reliability concerns. Now here we go to look at these packages, and now on the left this is us, you know, this is how we think, the rectifier people, and on the right hand side is more your thinking, or we hope that is more your thinking. So the first question, of course, that comes up with all these packages is, are you going to use wave or reflow soldering? So that's the first question coming up. The second thing, of course, what type of power dissipation do you have? The third thing is, how much money do I want to spend to get the power density and the PCB cost? And that is, of course, linked to issues like multi-layer PCBs and that type of stuff. So this is your decision. We have customers that are willing to use 4-layer PCBs with thermal vias. For other customers, the market is that cost sensitive that they will never even touch these things, and it will stay 1-layer with the bottom of the FR4 just as a big copper plate or just a few components placed in wave soldering. So everybody's different, so we cannot, we do not want to influence you. Also, the height is another thing. Everybody complains, but a lot of people route the high components on the bottom of the side where there are wave soldering. So in this case, the new packages are thinner or less high, but may not be optimized for wave soldering. So we can give a couple of rules here, consequences here, and then we'll go back to the package outline and do some product positioning here. When we talk about transient thermal impedance, TVS diodes are perfect. You can just put the die if it works in a smaller package. So this is just a perfect application for downsizing. The other ones are, of course, input AC to DC rectifiers, where obviously the surge is the dominating parameter, and the power dissipation in most applications is quite limited. So here's another opportunity to potentially do it. Obviously, temperatures are temperature, rectifiers are temperature-driven devices. So if we're really having a lot of current and a lot of power here, it becomes significantly more complex to downsize and to get the heat away from it, and it will depend on your design rather than us. Exposed packages can improve the power densities. We have them all, or we have them available and things like that, but you need to increase the cost of the PCB. And then one thing we would like to mention here, because that's not always so clear, is that reflow soldering remains very important in our business of rectifiers. A lot of converters or things like that, they have the storage capacitors there, the big capacitors, they have the inductors or the isolation transformers there. So there are bulky components there that are wave soldered and that type of stuff. So, that are wave soldering, I should say. This is an error in the slide I just see now. So wave soldering remains very important in the power management business. So we will continue to wave solder, and as a result, the older packages will still have a big benefit in those applications. And sorry for the error here, that is wave soldering remains very important in the power management business. So here we are. These are the packages in red, the packages we invested in last year, just that gives you an idea. And the green packages are the packages where we have available capacity. What does that tell us about the market? The micro SMA package here for the future actually is automotive driven. There's a lot of applications in automotive that use SMAs with very little or limited power dissipation. They can go like in polarity protection, especially if you use the polarity protection diodes after the TVS or after the protection. They don't see that many surges, they're low current. So a micro SMA is just perfect. I mean, obviously I'm saying the downsizing or automotive, because the distance between anode and cathode is 0.5 millimeters. So that means from a creepage and clearance perspective, it needs to work, or the package needs to work in a low voltage environment. The package is actually very small and it has a copper clip. So this is something really that is really an excellent feature, that we can make packages now that are this small, that are clipped on the top and don't need wire bonding anymore. This is great for failure modes and all kinds of other things, thermal things. So excellent package here, great future here. SOD123W, we also invested here. Obviously, it is smaller than the SMA, and in a lot of in some applications, when the when the power is not that high, you can actually also downsize to an SOD123W. It has the right creepage and clearance for 240 volt environments, so it can also be used in non-automotive applications. So also this package has a excellent future. The SOD123HE on the right-hand side here on the top line, obviously it's doing well and that type of stuff, but it's moving slower because for people to be able to use this package in power dissipation, they will need to go to more expensive PCBs. And this actually here is the issue here. Not everybody in the business appears to be willing to do so. So then we go to the bottom line, and to everybody's surprise, maybe that the SMB and SMC packages are doing extremely well and have recent investment. It shouldn't be a surprise, really. If you want to downside an SMB or an SMC, you can, but most people are using these things, SMB and SMC, the bigger packages, because they're already dissipating half a watt or something like that, or at least 300, 400, 500 milliwatts. Now, you can downsize or increase the power density, but essentially only on multi-layer boards, because if you use something like the SMPC in the middle and there are no thermal vias or that type of stuff, then you just the size of the solder pads that will determine everything, and then the advantages of this type of component are gone. Also the SMPC, and this is a problem here also with the people working, for example, in high voltage MOSFETs, the creepage and clearance, right? It's the distance between anode and cathode here is 1 millimeter. So if you are looking, for example, also for high voltage MOSFETs or these type of diodes with in these type of packages with exposed heat sinks, they become simply less attractive, because you need to really have 2 millimeters, and then the die size you can get in these type of packages is also not that fantastic anymore. So great package SMPC also for the future, but again limited to maybe non-rectifier applications, output rectifiers, and predominantly also in multi-layer boards. The other ones here, the ones on SOD128 and thin SMA, we actually ran long lead times on SMB last year and tried to convert customers to SOD128 and thin SMA because we had capacity there. It wasn't a success, or it could have been a bigger success. We were hoping for more. Obviously, the SOD128 has a lot of installed capacity or a lot of free capacity. Because the issue is, of course, that it doesn't have that many advantages over the SMA. Just the height and pretty much the thermal performance is not that dissimilar from it. So you can downsize an SMB sometimes to an SMA or a SOD128, but you can do the same to an SMA. So essentially, it becomes a commercial question that the people promoting the SOD128 need to compete against the SMA on price to get the volume going. And that doesn't seem to be happening at the moment, but it could in the future. Anyway, it's a popular package in automotive customers, and we are completely second sourcing. So we are still developing the entire product line also in this package. So that actually here, that is here, we're covering, as the Americans say, all bases. That means also these new packages, even sometimes they are more niche-y and that type of stuff. We're still developing the entire product range in these packages and that type of stuff. We think here that the rectifiers is essentially a business where service and that type of stuff is actually quite important, with the thousands and thousands of part names available, and that's what we like to do, and we like to do well here. So we're having the entire product portfolio also in all the new packages. Talk a little bit for the people that are not in surface mount, and here just a quick question here. All these old packages, what are we going to do with them and that type of stuff? There's going to be very little rectifier obsolescence here. Obsolescence is caused more by the front end rather than the back end. For example, we have less problems with than MOSFETs. For example, there are some MOSFETs out there, it's 6-inch, and people want to shut those fabs, or the MOSFETs are still on 0.35 micron or 0.25 micron processes. People want to get rid of that, and it's no longer competitive. Those type of things, and that's actually an introduction to go into the next step, the front end step. Those things are not so common actually for rectifiers. So the front end is stable and all these packages will be there. If you think about it, if you need a lot of power out of something, to put something on a heatsink or a device on a heatsink is actually not a bad solution. So that will be done for the next 30 years and you are safe on these packages also. The bottom ones, for example, these actual devices, they're still sold. There may be some surprises for some people, but actually there are a lot of applications where rectifiers, where there's not even a PCB, like a photovoltaic junction box, where all the connections are, for example, mechanical. So there's also a future here for actual devices in the future. So the only thing here is that not here because it's obviously not AEC-Q qualified. For example, MELs, but they're still around. They were, considered dead 30 years ago, but they're still going. And I've even seen a PCN for TO92 package last year. So those are the two dodgiest packages, and TO92 is not even a rectifier package. But the obsolescence is, caused more by the front end in our type of business than the back end. So let's go to the front end in this case. So what we're going to do is going to run through the front end processes for rectifiers. And we're not going to go into detail of this, but GPP in this case stands for glass passivated pellet, with a bit of a weird name. On the left-hand side is a planar device, and I think that most people with semiconductor backgrounds will be familiar with the planar constructions in here, but the GPP is a little bit of a different product here. So the GPP, what you see there is the green thing is actually glass. So the green thing is glass, the yellow thing is the contact area, and the blue thing is the oxide to provide other protection levels. And for the rest, of course, you have your PN junction. So the glass stands off a little bit higher than the wafer. That's why you need to have a specific dimple designs, what we call them, or the lead frames need to be adjusted for that. And what you see, if you look carefully here, is that on the bottom side here is that those grooves are very deep into the glass wafers. So in essence, there is very little residual material in this package to protect it from mechanically. So the GPP process is 35 years old, roughly, in that case. It has also evolved over the years and now become more complex, and it is our workhorse in the rectifier industry. So this is something we need to say. Both processes are there, but the GPP process is the workhorse. Hundreds of billions of rectifiers have been produced using this process by dozens of companies. And so that is something we need to clearly satisfy. I'm not going to go and go to the wafer fab process at all, but it's actually a really simple process here. It's actually available for you to study yourself. It has three photolithographic steps. So it is a very simple process. It comes in 4 to 5 inch wafers, and it has a long future ahead of it because it will not be beaten on price. So this is a possible effective process, and that's actually the main message we would like to give you about this thing, about this process. Now let's go and look a little bit more in detail about the rectifier processes. Before that, I'm not going to bore you. One of the problems we have with rectifiers is we have thousands and thousands of part names, and every month we add another 30 and 40, and then you go to big lists like this, and it turns people off. But these are some of the recent planar diodes which we introduced, 20 or 40 I believe, because it's 2 voltages and various packages and things like that, all 175 degrees C rated, also all from our planar fab, and you can see on the right hand side in all the surface mounted packages. We've actually introduced one in an actual package I've seen last week. So lots of products were introduced here, not the point here, but let's go and look at it in a little bit more detail. Now this slide, I'm going to have to familiarize you here first here. This PU3, the top thread here on the left hand side of the column, is a planar FET, and that's in an SOD 1 to 8. On the right hand side is the GPP. It says so helpfully under the name, and that's also in an SOD 1 to 8. Let's compare both. They're both 200 volt products. They're both in the data sheet. It says that they are 3 amps. And we have a number of specs which are actually very similar and things like that, as usual. And they're both rated at 175 degrees C. This is something I should tell you, that the GPP process comes in different variants, sometimes 175 degrees C rated, sometimes 150 degrees C rated. I should apologize for all our, in the name of the rectifier industry, for all our maximum reverse current specs, 2 microamp and 5 microamp here. I think we're all guilty of that in the rectifier industry. Having CPKs of 20 or something funny on rectifier currents. We'll talk on leakage current. We'll talk a little bit later about that. But unfortunately, that is something you don't always see or can judge in the data sheet. So if we're going to compare them here, then what we're seeing here is that the VFs here, if you look at the actual distribution here, of the left the planar, on the right the GPP, the blue things, you can easily see that they are, I would say, quite similar. What you're seeing here is that the leakage current, and remember our 2 microamp spec here, is 4 nanoamps and 10 nanoamps here for the planar device and for the GPP device. So they're far away, and of course they have no leakage current at all or to speak of. Then if you do the same thing at 125 degrees C, the VF here, fortunately, of course, has a negative temperature coefficient here, and of course the leakage current has a positive temperature coefficient here. Here you see that the GPP already has double the leakage current of the planar device. So the planar device inherently does have a lower leakage current here. The only reason why I'm actually including this slide here is quite simple. It is because you can see here the positive temperature coefficient of TRR. The TRR test conditions are also, test machines that are 40 years old, and as a result may not reflect your actual application, but this is what we use as convention in the rectifier industry. And as a result here, you can see that a TRR, or I should better say the stored charge, actually has a positive temperature coefficient, and that is not known to everybody. So I'm diverting 1 minute just to bring this to everybody's attention here. So if we're looking here at the planar device here, one thing I didn't mention, because the last thing wasn't particularly up to scale the last drawing where they were next to each other, is that especially these glass grooves here in between the die that we etch and where we apply the glass are actually fairly big, or fairly big. So what we call the die size also has what we call an active area. That means the area really used to that we can contact. So that is a big advantage of planar devices. So planar devices have a higher active area than the GPP process. And as a result, this one here is an SMB package. You can get a much bigger die or a much bigger current rating here into an SMB package. Obviously, this is just, you can't really get 6 amp out of an SMB package. This is, done because of the thermal resistance, but this is done especially to have a better efficiency. So these parts can be used to get a higher power density with a better efficiency in the circuit here. So the 6 amp at the 0.94 volt is actually a fairly good specification here in working. So this is why another advantage of the planar products here. We'll go to the summary after this slide. In the industry, this is just a cross-reference for these new parts. I included them. In the industry, there are tons of, there are a few Taiwanese and Chinese suppliers. They predominantly use GPP, just like Vishay. The people you see on the right here are more suppliers of planar die, or usually use more planar die in their processes. So here we go, and first and for all, I would like to apologize. I hope nobody dialed into this webinar for the silicon carbide information. I will talk about it for a second. So the 2 main processes for rectifiers are GPP and planar. Rectifiers are not only shipped by the tens of billions every year, but we are a 4.4 billion We are a 4.4 billion business according to the WSTS data. It's not 100% updated, but that's roughly what we expect to hope to end up with in 2021. And that is, of course, a very substantial business, and these are the dominating processes, predominantly the GPP process and the planar process. Rectifiers are low in any Pareto analysis of field failures, so normally we don't get a lot of field failures returned. Beware that we are always, shipping these things in the billions, and we're always some of the hottest components on the PCB. Because it's very difficult to reduce our power dissipation. They are very cost efficient, they're long established. There are different versions with DJ ratings, the way you saw them, oxides and a whole lot, and it meets most demands. But the planar process is more automated, and it may appeal to automotive auditors. So we are focusing planar processes predominantly for automotive customers because they sometimes think this is a better process to look at, even though we will always defend the GPP process internally. So it has lower leakage currents, that's for sure. It has automatic 175° C rating. It has a higher current density by package, and it also offers a couple of other features like higher voltages can be made, ion implantations, maybe for softness, and that type of features it also have. Will silicon carbide make a big inroad into the rectifier market? Maybe I'm heretic by saying no, or not that much, when the rest of the people always think they will. The VF of a silicon carbide diode is always quite high, or is higher than silicon. It has a positive temperature coefficient, which doesn't help rectification issues, and its main issue is that it has very small die sizes, which means that if there is a surge to combine with this positive temperature coefficient, it is not terribly stable. Or it doesn't have very good surge capability, and as a result, in a lot of applications there are surges. So we don't see this massive replacement of silicon carbide, or replacing silicon. But of course, there are a couple of things where it's used very often, and that is of course in hard switching applications where it doesn't have any minority carriers, and as a result, it can potentially increase the efficiency. But the only thing is power factor correction is the most long-term famous hard switching application, or at least in continuous induction mode. And so it has been, but that's already going on for 25 years, and in that area, silicon carbide uses about $100 million, $150 million of revenue in that area. We obviously acknowledge that that silicon carbide MOSFETs are opening all kinds of new opportunities, in this case topologies, where silicon carbide can benefit, and also it seems to be very preferred in automotive application. One thing I would like to say to you though is that this week you always look at who are we competing with webinars and what's going on. There's another webinar about the bridgeless totem pole PFC topology, and there's a lot of you see one every week. It increases the price of what we do with a bridge probably by a factor 10 or 20. I don't really want to know. We don't market in the planar process these LLD diodes very well, but actually every GPP diode has got a VF of 1.05, 1.1 in that area, and actually you can go down with planar process to 0.95. So if you are really squeezed on efficiency, and if the 0.6% that the bridge actually causes of efficiency losses that the bridges cause is important for you, please talk to us, for about these LLD diodes, because we can maybe help you. The last thing about this overview of the processes I would like to say is that what it says is that there's going to be no market consolidation here. So that means that there is no synergy between these processes and any other processes in power management. As a result, it's going to remain an industry dominated by people, Asian people, Taiwanese people, or Chinese people in the long-term future, and because there is no synergy in the front end with other major power management topologies. A few more slides here before we stop here. One or two more slides in defense of the planar Schottky diode. So the planar Schottky diode, we offer both, right? So we offer both a trench and planar technology here. So Taiwan Semiconductor has both. Also, how to choose a Schottky diode when there are more than 1,000 part names. It's becoming quite complex, right? I think I once looked in the DigiKey catalog and they have more than 10,000 Schottky diodes or something like that. So it's becoming an art. On the left are you, the user. On the right are we, the supplier of the material. And we need to match all your requirements with all our technologies, plus also some of the stuff on the bottom there. So of course you're interested in efficiency, but you know that will come at a certain cost here. We're also going to look at service here really because we had a difficult year in power management on deliveries. So, but the technologies you know can make a difference on how you on lead times and that type of stuff that is available here. We'll explain that a little bit more. Then you, of course, have to ask the question, is thermal runaway relevant in my circuit? That is an important question. And of course, you have to also decide what DJ and delta DJ you want to accept and what your reliability targets are for your application. So in this case, we then choose the 150 or 175 degree C barrier material. We choose planar or trench technology. And of course, also the choice of package is critical in these applications. All the package choices we shown before on the back end, the same thing is available here, whether it's wave soldering, you know, the multi-layer boards, exposed pads, power density is also important. And actually also here, I should mention that the way you answer this question actually depends on the voltage, whether you're using a 40 volt or a 200 volt diode here. So this is no longer an easy subject. It becomes just, you know, becomes quite complex actually to choose a rectifier or a Schottky diode, combining the advantages of the technology together with the commercial aspects here. So we helped this you can download from our website, but I'm just putting the highlights here to tell you what's available on potential help on sourcing these Schottky diodes. So a couple of things here, the marketing conventions on Schottky and the definition of maximum TJ. So, you know, suppliers have some liberty here. Of course, you want the maximum TJ to be linked to high temperature reverse bias testing or at least the AEC-Q and that type of stuff. But, you know, in general, barrier materials are grouped in 150 degrees C or 175 degrees C groups. And there is some liberty in doing that. Thermal runaway is explained. Of course, is this important or not? It will become, you know, it's always been there. You can put every Schottky diode in thermal runaway if you just choose the right, or if you want to call it the wrong conditions. It can always happen. But of course, it will happen more if you have higher voltages and higher TJs and junction temperatures. The reliability and a TJ of a Schottky diode here is something, you know, usually in a rectifier, of course, we say, hey, 175 degrees C TJ is better than 150 degrees C TJ. In the case of the Schottky, you're maybe just testing two different barrier materials, right? So it might be a different world in the Schottky. So, you know, second sourcing Schottky is becoming quite complex, and search engines do not help here to catch the diversity of a Schottky. So, in the case of a Schottky diode, you still need to look at the data sheets and not rely on search engines to get an equivalent. So, front-end technology and thermal runaway, definitely. If thermal runaway is an issue for you, then you want to use trench Schottkys. Back-end technology, you know, can also keep the TJ a little bit lower and help on thermal runaway. But the main thing is, of course, on the front-end technology, you know, you want to use trench Schottky if thermal runaway is an issue, or if you're close to the thermal runaway point. We also wrote something about the Schottky have a TRR. Of course, there are no, you know, it's just. There are no minority carriers in a Schottky, so essentially it doesn't have a TRR, but you can always inject them via the guard band, but usually a Schottky diode does not have a TRR. and we lived like that for the last 30 years. The 2 points here I highlighted here, that here is the temperature coefficient of VF between planar and trench Schottky. Because in a lot of searches, the initial VF, if we compare apples to apples, or at least at 25 degrees C, the trench Schottky will always look much better. But planar Schottkys have a much better temperature coefficient in general. So if you start at 100 degrees C, you'll see that the planar is catching up with the trench, or is close or similar at least. So please, in the future, everybody compare the VF of diodes at higher temperature in the curves. That is one way of doing that. The second thing is the supply chain of the trench Schottky. Planar Schottky is actually in separate fabs. It's in its own private world, if you want to say, and people make the planar Schottky, in dedicated fabs. Trench Schottky is competing against other things in a wafer fab. It's competing against MOSFETs and other components here, and it usually has the lowest revenue per wafer here. So that is something we see a lot in the supply chain of trench Schottky. It is just less a reliable point of view of deliveries and commercial aspects here, because it is competing in fabs where actually you are competing on cost per wafer or revenue per wafer here. So don't switch to trench Schottky unless you really have to, because of thermal runaway, or because you're really looking for efficiency gains or that type of stuff in certain applications here. Keep both in the back of your mind and evaluate them neutrally, and see also what your purchasing department may tell you about the different comparisons between the two. First and for all, we'll stop it in 3 or 4 minutes here. We've got 3 slides on the on zero defects here. It's important here. I'm bringing this up because the rectifier world in the future will be more of an Asian world, and with those people dominating the market. And as a result, maybe you don't know all of them, or maybe some of these suppliers are just unknown to you. So most important things here on rectifiers there are 2 absolute maximum ratings really. That is the surge current rating and the maximum voltage here. A little bit more about the surge current rating and what's going on in this business. It's guaranteed by design and not tested in production. So the test times are too long, and it's not, everything heats up and you can't do any reliable testing afterwards anyway. So the 8.3 millisecond specification, or sometimes 10 millisecond, becomes the days of linear power supplies. Yes, 40 years ago, we haven't changed for that for a long time. So, but now in this data sheet of these new FER components, we see for the new ones, we are always putting in 1 millisecond. This is okay because, most surges are usually less than 1 millisecond. So this gives you a more reliable value. If you see the old ones, of course, you can always do I2T conversions, but always be aware that they are an approximation only, because the VF changes with the current, and you may not be on the same part of the transient thermal impedance curves. So this is important to know. What you do need to know, however, is, and this is invisible to you, is that solder voids impact the failure rate. So if there is a failure rate, it means usually, not always, but the biggest thing you start to look for if somebody reports a surge failure is the solder voids. And there you really need to know your supplier, and in this case, whether their soldering processes eliminated solder voids. We have done that, but maybe not everybody in the Far East has done that. So this is something you need to be aware of. The second thing here is, I'm gonna load everything at once here. Sorry if the screen is not stable for a second. Is that we already mentioned it. We have 5 micron IR test limits, and we have 10 nanoamps of actually the distribution, the typical distribution here. So the CPK becomes, irrelevant, or the test spec is irrelevant, or the datasheet value, I would say, is irrelevant here. So rectifiers, that's why all rectifiers need part testing, part average testing here. because everything that is outside the normal distribution here is a potential source for long-term field failures. There could be minor cracks in the glass, in the die, and that type of stuff caused by the sawing, and so on. So there are parts that are outliers out in the normal distribution that need to be eliminated. Not everybody does this in Asia. You better need to find a supplier, or I would recommend, getting suppliers that are 100% path testing, which is needed for automotive customers anyway. So yes, and the last slide here before I'm going to look at your questions and close the webinar is, of course, absolute maximum ratings. There are the breakdown voltages in the surge current. This is something here that, don't take yourself some space here where the resistor is clamping or something like that, because some of the norms, especially the lightning norms, you could say that lightning is an anarchist. It does not follow the rules or the norms. So you might just see that, you better have an extra margin here, or if somebody, reduces the die size, then your robustness actually against lightning strikes might just actually be reduced also. So this is something you need to be aware of, that voltage spikes and lightning and so on do not follow rules. So have enough margin and know who you are dealing with. How to interpret TJ Max? It's I always take the example that is 149 design where junction temperature becomes 149 degrees C. Is that better than 151 degrees C? If the TJ Max is rated at 150 degrees, obviously the answer is not much really. So be conservative in your design. We already mentioned you need to know about path testing. You need to know about solder voids. And then, some of the mechanical components here, because we're talking about 12-inch fabs that cost $1 billion, and automated the wafer fabs and all that. But some of the components here, bridge rectifiers and that type of stuff, still have manual operations in them. And there are bigger suppliers, with differences in bridge suppliers. For example, people want to save some money, and instead of a 0.8 millimeter rectifier, save some copper and ship 0.7 millimeter wires. These things happen. You reduce a bit of copper in a bridge rectifier, and those things are all things that I've seen happen in that type of stuff. So here, for these type of components that are the older component, actual bridges and that type of stuff, you better know your supplier here. And of course, the final thing is that automotive-focused suppliers have the systems to support the zero defects, and that's what we are focusing on. This actually ends the webinar. I hope it was not that too much information. And if you do have lots of questions, send us an email. The world does not work without rectifiers. And now I am going to immediately to see if I can see some questions, because there was a question and that type of stuff. Questions. How the exposed paths, I think the exposed paths are connected here is to anode or cathodes, or I'm not sure if I can. I have to apologize here because the question function is not. So there's a gentleman here that has a question here about the chip thermal connected here, and I cannot read it here, the question here, but I will follow up separately. So I will reply to you in a separate email. Sorry, the question, I cannot see it here 100%, but we will reply. Okay, in that case, we have, we are 55 minutes in. So in that case, I would say thank you, everybody, for listening in today. Thank you for the interest in our company. If you have any further questions, please send us an email. You will get a follow-up email with the materials here, or with a request for the materials here. You can request them, and so please use that function here to get more information about our company and submit any further questions you may have for the about the rectifiers. Thank you very much for your interest, and I wish you all a pleasant afternoon, or I understand some people in Asia a good night, and some people in the US a good breakfast or a good morning, I should say. Thank you very much and have a nice day. Goodbye.